Hello, I'm Jackie Guo, and I'm an incoming senior at the University of Texas at Austin in the major of chemical engineering. And this summer, I've had the fun to be part of the Department of Pharmaceutics in the Zhang Laboratory and work on dendrimer lipid nanoparticles. These are the people in our laboratory. So thank you so much to the four individuals I've shown for getting me accustomed to the laboratory procedures and to giving me a lot of advice for my future career. A special thank you to my PI, Dr. Zhang, and my mentors, the Jean. None of this would be possible without you guys. To begin, there are a lot of applications to mRNA-based therapeutics. One that's the most commonly known is probably COVID vaccines. Through Pfizer, Moderna, etc., mRNA just has a lot of potential for treating diseases. The main issue is that mRNA is difficult to deliver. This is due to them being large, hydrophilic, and negatively charged, not good criteria for crossing the cellular membrane. This is where the lipid nanoparticle comes in. And the main thing that we focus on is the ionizable lipid, as it is the key part that protects the mRNA and helps the mRNA get into the cell, into the cytoplasm, and transcribed for the proteins for our body. There are diverse amounts of lipids already out there. As can be shown, there are saturated, unsaturated versions, and different components that can be played with. However, in our case, we are using the dendrimer to improve the lipid nanoparticle. The goal at hand is to create a library of dendrimer lipid nanoparticles. This can mean varying forms of lipid conjugations or different generations, different sizes. There's a lot of ways to play with the dendrimer lipid nanoparticle, as can be shown through the dendrimer. So in the dendrimer, there's an initiator core and then repeating generations that grow from that core. And they're essentially arms of that core that are then multiplied and reach a surface terminal group, as shown in pink. The great thing about the dendrimer is that it's structurally symmetrical and it has high uniformity, which is really rare in modern day molecules, as this allows the dendrimer to be modified in ways that is uniform and varying as it can adapt to various environments. For my case, the core that I began with is core 2, which is the beginning piece shown below. The first generation has 2 arms, and the second generation ends up branching into 4 arms. The yellow box shows the original core piece and the eventual branching, as it can be a little hard to find the core within the branching. For our case scenario, we only went to the second generation. However, there has been multiple studies where it goes all the way to the 6th and 8th generation, which are very large molecules. And then once those core dendrimers are developed, we're able to add a lipid tail to them, which it forms the lipid of the dendrimer lipid nanoparticle. In this case, it's the most simplistic form of the core 2 itself. There's a 0%, 50%, and 100% variable. The 0% is the original molecule, and then the 50% is that one additional lipid tail, and 100% is a 2 lipid tail attached to the original core. As in the case of a second generation molecule, there'd be a lot more branching and a lot more different tails, as the 50% would be adapted to the 4 rather than the original piece. For the separation methodology, when the reaction is set up, there are different ways to get the excess reagent and solvent from the product. Due to the dendrimer only being able to reach 40 degrees Celsius, a lot of the solvents would not be able to evaporate in our general atmospheric pressure. So the rotoevaporator allows the vapor pressure to decrease within the system and allows the solvents and excess reagents to evaporate at a much lower temperature, which is good for our product. The thin layer chromatography, the TLC, is just a small scale version of the prep TLC mentioned, and there will be a prep TLC shown later that allows the dendrimer lipids and dendrimer lipids to be separated, as there's different polarities within the product. The results shown are how we verify the synthesis of the dendrimers. This is with NMR. So the main thing from the core 2 to the core 2 first generation is that there's an intermediate product of an OME group. So the arrows are showing how it is very present in that first intermediate product and then not present at all in the final C2G1 form in green, which is is the key aspects that we're looking for, the key structural changes. And then from the green to the red, it shows that there's a decrease in the height of some peaks, which is the impurities that are in the sample. And this is just showing that the C2G1 has continued to be purified and went from a 95% purity to 96% purity from the calculations of the integration of the curves. Additional results, this is a crypt TLC form, is the synthesis of the dendrimer lipid nanoparticles itself. So at the starting point, that is where the item will be most polar, and at the very end, which is the arrow of the lipids, will be the most non-polar. So since this is for a core 2, generation 2, 50% conjugation, we would expect the product to be somewhere in between, as the very end would be the lipids and the very bottom would be the unreacted dendrimers. So it is using our fundamental guessing that that bold line is where our product is, as it is probably where most of the product in general is, and it has mid-range conjugation, which could be 50% conjugation. Not quite sure why there are multiple bands, but that could be something further looked upon, as well as product yield is not the best, roughly 4 to 8% from an original 200 milligrams, and that is not the best product yield. However, that can be worked on, as we're trying to use a reverse plate TLC, which is something that is that we're just beginning to look into. As final results, these are little clusters of different dendrimer lipid nanoparticles that I was able to synthesize, and that Zhang at the moment is able to test in vitro in cell cultures whether there's an effective delivery or not of the lipid nanoparticle. In conclusion, I have greatly appreciated the efforts and the care that this lab has put into me and has allowed me to grow in my educational pursuits. Additionally, my roommates have been a great part of this experience as well, and this program itself has been extremely enjoyable and really eye-opening. So thank you so much and have a great day.